Good morning to everyone. Today's subject is fluid mechanics and hydraulic machines. My roll number is 20951 80314. Today's topic is boundary layer rake of pitot tubes for flight testing. I am from mechanical branch. Abstract. A new boundary layer rake has been redesigned and built for flight testing on NASA Dryden Flight Research Center F-115B flight test fixture. A feature unique to this rake is its curved body, which allows pilot pitot tubes to be more densely curved in a near wall region than conventional rakes allows. This curved rake design has a complex three-dimension shape that requires innovative solid modeling and machining techniques. Finite element stress analysis of the new design shows high factors of safety. The rake has passed a region test in which random vibration measuring 12 grams RM 12 RPM was applied for 20 minutes in each of three normal directions. Aerodynamic evaluation of the rake has been conducted in the NASA Gen Research Center 8 into 6 supersonic wild tunnel at Mach 022. The pitot measures from the new rake agree with conventional rake data over the range of Mach numbers tested. The boundary layer profiles computed from the rake data have been shown to the standard logarithmic law profile. Sink friction values computed from the rack data using the Careless plot method agree with the Pritt's tube results and the Van Rest second compressible sink friction correlation to approximately 5%. Introduction. A new boundary layer rake has been designed and built for the flight testing. The flight fixture F1. The 15BF is aerodynamics and fluid dynamics research tested bed at NASA Dynamic Flight Region Center, Edwards, California. Figure 1. The F-15B FTF is in flight. The FTF is the black vertical flame link shape mounted on the center line of F-15B lower fuselage, primarily made up of composite materials. The FTF was designed for the flight research at Mach numbers to the maximum Mach of 2.2. The new boundary layer rake has been designed for the in-flight evaluation of skin friction gases. In this upcoming experiment, the skin friction gases will be mounted on the surface of FTF together with the boundary layer rake and piston tube. The flight conditions will be chosen so that the flow over the FTF approximates simple fate plate show follow, allowing good estimates of sink friction to be obtained using Carlsson plot method 2 and the piston tube method. These estimates will then be used to evaluate the performance of the skin friction gauges in flight. Rack fabrication techniques. Although the curved rack concept described above is quite simple, the mechanical design and fabrication of the actual hardware were very challenging. The three-dimensional design consists of a large number of curves and angles. In addition, the actual rake needs to be rugged to withstand supersonic well tunnel and aircraft operations and provisions needed to be made up for routing and installing the pilot tubes. Continuously innovative three-dimensional solid modeling and machine techniques were required. Starting from a three-week conceptual sketch, a three-dimensional solid mold was concentrated using the three-dimensional soldering modeling software. The same software was used throughout the entire design and machining process, ensuring the accurate machining of the rake from the three-dimensional solid model. The actual rake body needed to be strong and streamlined, and the provisions had to be made for the installation and routing of stainless steel pitot tubes. Flight qualification analysis and testing. To determine the structural integrity of the new rig, finite element stress analysis was conducted for the both wind tunnel and aircraft operations. Factors of safety were computed from the solutions of finite element analysis. Also, a vibration test on the rake was conducted at NASA Dryden. Finite elements stresses analysis to qualify the rake of supersonic wind tunnel operations. The computer solid model was analyzed using the Compo COSMOS works finite element analysis package. Investigate for flow theory was used to obtain the pressure distribution of the rake body. In the finite element analysis, the pressure were specified as boundary conditions, while the base of the rake was held readily fixed. Wind tunnel testing of rake. To evaluate the aerodynamic performance of the new rake design, two different boundary layer rakes were separately tested in two wind tunnel tests. The newly curved rake and rake respective of conventional design. The wind tunnel test were conducted in NASA Jennings SWT. The first test used the new curved rake. The second test, which took place on 1 week later, used the conventional rake. The conventional rake was used as a check for the new rake. Nearly identically wind tunnel flow conditions were used for the both tests. Both of the tests were conducted for Mach numbers ranging from 0.05 to 2.00. Instrumentation and data equalization. Two instrumentation systems were used to measure the pressures and temperature of the wind tunnel test. An electronically scanned pressure ESP system and an isothermal thermocouple junction reverse block. All pressures, including the boundary layer rake pitot pressures, the wall static pressure and the wind tunnel total and static pressure were measured using ESP system. The ESP system was configured with 30 to 1 BF in two absolute pressure calibration and unit and differential pressure method modules. The resolution of the system was configured to be 1000 counts. Test conditions. During the test, the tunnel total temperature ranged from 630 Rg to 500 R. The tunnel total pressure ranged from 25 25 lbf in 2 absolute to 14 2 absolute mark. For each test, approximately 4 hours were needed. Thank you. Thank you for giving this wonderful opportunity to share my views. Thank you, one and all.